Well, welcome to week 11, folks. We're just waiting for the clock to run down to 6 o'clock. And there it is. Looks like we can get started. Welcome back, folks. So for today's week, or today's class, we're going to be working on section 7.3. We're on the third example. And probably we'll start section 7.5 as well today. These will be the main two sections we'll be working throughout this week to stay caught up with the syllabus. But the main announcement is we have our third exam now fully posted with the information, the review problems, and the list of identities that are needed to be memorized. This list got a little shorter than the earlier draft that I first showed because our third exam is just going to involve these three sections, which seems about right since exams 1 and 2 also involve just three sections. So I felt like that was a right number. Also, section 7.2 we've just completed last Wednesday. So we'll discuss a little bit more about exam 3 when we come back on Wednesday. But my standard comment is the number one way you can prepare for this exam is to work through these three sections. Even if one of them went late, I'll still accept it. And once you get these solved, I'll be working on getting things graded as soon as possible going into the weekend. But any questions at all, folks, to start us out today? Okay, well, as far as the information on the review problems, it's kind of the same deal that we saw on exams 1 and exam 2. There's a slight change with version 3. So just to take a look at it briefly. Version 3 is usually problems out of the textbook, but just to give a little bit more variation so it didn't feel like you're looking into the homework problems all over again, I wrote custom problems right here. Problem number 1 on the first version of the exam 3 review is just a refresher on this is major stuff that we need to be ready for when we solve the section 6.3 problems. And this is kind of tricky because I'm not allowed to post formulas on the third exam as per the math department rules. But I didn't consider this to be a formula. I felt like it's more just information. So this is included on the third exam on the very front page. So filling out this is just a way to get more familiar with it, which you'll need for that third exam. So I have solutions to problem number 2 at the very bottom of the document and the whole table as well. And the rest of the problems are the standard textbook exercises like we had for exam 1 and exam 2. So these are primarily just odd problems. I don't think there's a single even in that list. So you can see the back of the book for solutions there. Then the version 2 for the sample exam 3 review problems, takes a lot of words to say, is just the lecture notes. It's not every single problem necessarily. In some sections, I did take out a couple problems, but it's just the lecture notes problems I felt like would make a good exam problem. So you can see back into the lecture notes the way we solve these for a quick solution. So really just kind of the same pattern as we did before, but make sure you take a look into this right here. Practice writing down the identities, kind of like practice writing down the unit circle as kind of a warm up to when you study these problems or do your homework problems, and you'll be ready to go for the upcoming third exam. I think that's pretty much my full set of announcements to start us out. Any questions or comments before we jump back to 7.3? Okay, well, in 7.3, we're looking into a whole lot more identities. 7.2 ends at the sum and difference identities, which I sometimes abbreviate to say the addition formulas. But here we looked into the double angle identities and the half angle identities. We're on example 3, but just as kind of a warm up on what we did before we got to that point, here are the new identities at the top of the notes. So this is not going to be on the third exam. This will be a final exam material. There's the double angle identity for sine, cosine, and tangent. They're proven using the addition formulas. And to do any one of these three identities, we just had to take the cotangent value, use that to solve for sine and solve for cosine. So really, these are the Pythagorean identities that we had to use just to start the problem. That part right there is definitely exam 2 material. Then we did a long derivation. This one was kind of nasty, but it was mainly because the next problem was like a 10-minute problem at minimum. And we were like the last 5 minutes of the class. That's an interesting identity because to prove just this identity, you use the addition formulas from section 7.2. Then you take the double angle identity, use another Pythagorean identity on the yellow highlighting, and you get this new complicated equation right down on this line. But if you go and solve this equation for cosine theta divided by 2, you get these kind of identities. In place of theta, I have alpha, but same identity if we change the variable. So these are the last set of identities, the half angle formulas. Actually, there's more down below, but one thing we'll make a note of is the very last identities we see on this document is just taking any one of these two right here, squaring them, and giving them a new name, calling them the reduction formulas. So this is where we close the lecture on Wednesday's class. This problem is pretty tricky because we are trying to calculate the half angles for sine, cosine, tangent, and cotangent, which use pretty complicated looking formulas, but actually the formulas themselves are not the most complicated part. The tricky thing about all this is we're given information on an angle theta to start out. That's constrained between 3 pi over 2 and 2 pi. So we started by just plotting that angle theta between 3 pi over 2 and 2 pi. Here's theta. But when we go to calculate sine theta divided by 2, we have to decide on a sign, positive or negative. So we had to actually place theta divided by 2 inside the inequality. I believe the major thing we did was we took this, divided all three sides of this inequality by 2, so theta over 2 fits into the identity, and we found theta divided by 2 is now in quadrant 2, whereas ordinary theta was way over here in quadrant 4. So we have to use both pieces of information here and here to solve this entire problem. Trickiest thing about this is resolving the negative signs. So after that refresher, we have information on the sine value. That's kind of unfortunate because we need cosine here, here, and here. So now we need to compute cosine value itself. Once we have that, we can start using the formulas. But this just becomes another use of the Pythagorean identity. If we have a sine value, we can calculate any other trigonometric function. We're just going for cosine. So let me put a quick border here. And let's start by writing out cosine squared theta plus sine squared theta equals 1. Let me remember that when you write sine squared, you should put an angle inside there. There we go. That's now correct function notation. Plus sine squared of the angle theta equals 1. So that brings this sine value into the equation. We have cosine squared of theta plus sine squared, which is just squaring negative 1/10, is equal to 1. And then we can quickly solve for cosine squared. So writing this out, cosine squared theta plus 1 over 100 after we square is equal to 100 100ths. We usually take this step to just get the least common denominator in line. So we can subtract 1 100th to get cosine squared theta is 99 100ths. And then take the square root. We'll have cosine theta equals positive or negative root 99 over root 100. But because this is the angle theta, we go back over here, and this information is what's relevant. Theta is way over here in quadrant 4. Cosine value comes out as positive, so we're picking the positive sign on this one. Let me target the highlighting a little bit better. Just the positive sign on this one. And while we're at it, we might as well reduce square root of 99 because we're plugging in that value in 3 different spots. The simpler we make it, the more worthwhile it's going to be. So just on the scratch work, root 99 becomes root 9 times root 11. So this is just going to be a 3 root 11 up in the numerator. So finally, altogether, we have cosine theta equals positive. I'll put the plus here just to emphasize we took the positive root. 3 square root 11 over 10. Once we have that cosine value, we're just going to plug it into these 3 different identities, which will do the first 3 parts right here. But any questions at all, folks, running through this first initial step? Just trying to get as much space vertically as we can on this. Okay, let's go left to right, starting with the sine theta over 2, working cosine and tangent, and get the values. One thing, again, we have to be excruciatingly careful with is when we talk about theta divided by 2, we're over here now in quadrant 2. We took this identity, divided it by 2 to get the 3 pi over 4 and pi, those two constraints here and here. So now for sine theta divided by 2, citing the identity above, we have sine theta divided by 2. Let's color code that just for emphasis. At its heart, it's either positive or negative square root 1 minus cosine theta, then divide by 2. But on this one, because theta over 2 is here, sine takes on this positive value somewhere on the y-axis. So we're going to take the positive root on this one as well. So it's going to come out positive. I'll just write that sign once to emphasize we took the positive root. Square root of 1 minus, and whatever cosine came out as from the work on our first step, we just substitute in right in this position. So 3 square root 11 divide by 10, and let's make that square root symbol a little bit longer. I never seem to write them long enough. Divide by 2. So we're just about there. What makes these kind of tricky problems is not the identity. We're done with the identity going from here to here, plugging in the information. But now we have to simplify it even further. The sign as well is not an easy one to resolve. Any questions with any of these elements so far with the sine theta divided by 2? Okay, one thing that's kind of interesting that we'll take advantage in just the next problem is, notice the pattern. Any one of these identities, all you're effectively doing with the angle itself is taking whatever the input is and doubling it. Double the angle, which makes the name of it kind of unfortunate. It's called the half angle formula. That's just because you start with half the angle, but then when you use the identity, you double it. 2 times alpha over 2 is just alpha. Likewise, going from here to here, it was theta divided by 2, but we double this, and we get just theta. Then going from here to here, only thing we did was make a substitution. And our goal now is to simplify this as much as possible. I think the cleanest way I can simplify is getting rid of that 10 right here in the numerator's denominator, making it not a complex fraction. So let's multiply by 10 over 10. We have square root. Distribute that 10 inside that group, and we get 10 minus 3 square root of 11 divide by 20. And now I made that square root symbol too long. Let me make that seem less awkward. This simplifies to the root of the numerator, the square root of 10 minus 3 times the square root of 11. So a pretty complicated root in the numerator. Let me fix the 3. And the denominator, we're taking the square root of 20. And if you left square root 20 here, that would have been totally fine. But it's not a bad habit to just reduce that where we can. Root 20 turns into the square root of 4 times the square root of 5. So that's a 2 root 5 in the denominator. And 2 root 5 is what goes in. I don't see a clean way to simplify this any further. This would be where I would leave this problem. I wouldn't even worry about rationalizing the denominator when you have something even more funky going on, a square root with a square root inside the original square root. But this is a pretty simplified expression for sine theta divided by 2 in this problem. Next, we want to do it all over again for cosine version, cosine theta divided by 2. But any questions or comments at the moment? Okay, this is the point at which this whole problem becomes a little bit more friendly. Notice the big observation on the original three identities here. The sine alpha divided by 2 and cosine alpha divided by 2 identities are almost completely identical. The only different version is when you use the sine value, you plug in a minus right here. And if that's the one and only difference, doing it again with a plus, it's going to look almost identical throughout here. So if you've done the algebra once, you've essentially done it twice. You're just going to take this sign and flip it to positive. So let's just write out the details to see what it looks like. Don't forget as well, we have to resolve, is it positive or negative? That's another tricky element. But the major algebra that we went through is essentially over at this stage. For the second thing we're calculating, since there's a lot of math here, let me box out. This is one part of the answer we wanted. The next part is cosine theta divided by 2. It's either going to be positive or negative, square root 1 plus cosine theta divided by 2. So here's that key difference. You're practically doing the same thing for sine theta divided by 2 and cosine. Next major thing is we have to see what quadrant theta divided by 2 terminates in. We're in this quadrant, and in this quadrant, cosine theta divided by 2 is a negative version. Whereas for sine it was positive. That means we have to pick the negative root on this one, which seems strange because remember, cosine theta was positive, but that was a whole different angle. We have to use the actual angle that's the input to our function, theta divided by 2, to get the negative value over here on the x-axis. So now that we've resolved the sign, this turns into equals negative square root 1 plus 3 root 11 tenths divided by 2. It's the same exact thing as before. We just have, in place of the negative, a positive sign. So if we were to multiply by 10 over 10, just like before, let me make that look like a 10 first. We would get exactly to that step with a plus right where the red dot is, which means our answer becomes exactly this with the positive, if I can get the mouse to hold still, right where the red dot is here. So let's just jump to that answer. There's no reason to reinvent the wheel, essentially. This becomes negative root 10 minus 3 root 11 over 2 square root 5. So that's our second answer. We have 2 more to go, but not as bad to getting through the last ones. Any questions so far on either the sine or cosine version? Okay, I mentioned before that there's several different identities for this in the book, but this one is often considered to be the nicest, cleanest version of the half-angle identity for tangent. What's nice about it is there are no pluses or minuses whatsoever. This one's fully resolved. It'll give you exactly what you're getting based on whatever your sine value was and your cosine value was. And one thing that's nice about this is it simplifies really, really cleanly. You can solve tangent alpha divided by 2 or theta divided by 2 like in our problem by taking this chunk, the sine version, divide by this chunk, the cosine version, then simplify that. And it's a lot of work to simplify it to something nice that doesn't involve a square root with a square root on the inside. This seems counterintuitive because when we did this way on the top of the notes, let's take a quick peek. Way over here, when we did the double angle identities, sine 2x, cosine 2x, we mentioned if you have the sine value and the cosine value, doing tangent 2x is easiest just by taking sine divided by cosine. But that's only because the sine and cosine values were pretty simplified on their own. That's not the case for our problems. Our sine and cosine values are complicated looking things. They kind of hurt your eyes just to squint at them. So that's where this identity at the very top begins to shine. David says, in the cosine version, isn't it supposed to be a 10 plus? Oh yeah, thanks for spotting that, David. Good eye. I took my idea of copy it a little too literal. You have to copy it with a plus sign, just like you said. So correction for the record here, that should have been a plus. Yellow highlighting was supposed to save me on that. To match up with the plus up above. Thanks again for spotting that. Other questions or comments at the moment? Okay, so with that correction there, let's now turn over to the tangent theta divide by 2 problem. This one is not so bad. We say tangent theta divide by 2, just so that we're not dividing these large things and then trying to somehow simplify them. Let's take this as sine theta divide by 1 plus cosine theta. Might as well keep that in blue just for emphasis. Sine theta value is given right here as negative 1/10. It's over 1 plus the cosine value. Down here, 3 square root 11 tenths. And now we're done with that identity. Let's zoom back in a bit so we can focus on the algebra. Here's the identity again, just copied down. We have to simplify this down, but this is a lot easier to simplify, I think everyone would agree, versus trying to simplify a fraction made out of these things. Really, all I would do to simplify this is just multiply by 10 over 10. Having trouble with the number 10 today, writing it out, there we go. We have to use the distributive law in the denominator, but across the numerators, it's negative 1/10 times 10 for a negative 1. And the denominator will get 10. Then the denominator eliminates, so it's just plus 3 root 11. So that finishes off the tangent theta divide by 2. We mentioned before in class, this is an okay stopping point. And just to emphasize that, let's leave it in this form this time, which is kind of nice because if you go to the next value, the cotangent theta divide by 2 up here, all you have to do is take the reciprocal of the tangent theta divide by 2 value. So in one step, cotangent theta divide by 2 is reciprocal of what we got for the tangent value. So it's 10 plus 3 root 11 over negative 1. Here, when you have something just divide by a negative sign, it's a good idea to just distribute into the numerator. So the overall result is negative 10 minus 3 root 11. So that's our last value for cotangent. So this one turned into kind of a cloud of algebra. The initial step was right here. Then starting right here, let's put a little star on it just to help our eyes. This is where we're actually using the identities on these 3 big ones. No real big identity for cotangent other than the fact that it's just the reciprocal of your tangent value. So that's how to do the half angle identities. They're pretty tricky because there's lots going on with the identities themselves, but just starting them out, making sure you get the right sign in, it's not too bad to start. Any questions at all before we try them again? Okay, another great use of the half angle identities is we can calculate some pretty interesting angles now. Just like when we had the sum and difference identities way back in section 7.2, we were able to calculate things like cosine pi over 12 or maybe sine 8 pi over 12, things like these. We can also calculate things like sine 9 pi over 8 in a really fast way now. So just for the sake of practicing these 3 identities one more time, we're going to focus on the sine one. We'll do a full evaluation sine 9 pi over 8, going for an exact value. First thing we should do is figure out where our angles are going to end up. So here's our unit circle diagram. Not the best circle of the day, but we got across daylight savings, so we're doing pretty good, I'd say. Plotting 9 pi over 8 is kind of tricky, but just keep in mind that's pretty close to pi. And pi can be rewritten as almost there, 8 pi over 8. So if we rotate just a little bit further, we would be over here at 9 pi over 8. So that's the angle we're dealing with. When we go to use this identity, it tells us we're going to be using the negative sign. So sine 9 pi over 8 is less than 0, so we'll be using negative. So let's start off just writing down the identity. Sine 9 pi over 8 is going to be plus or minus the square root 1 minus cosine. Let's leave that blank for just a moment. And then divide by 2. But here's the next big takeaway with this. When every time we go to use this identity, we take this angle, whatever it is, and double it to get the angle alpha on the inside here for cosine. So multiply by 2, or what we said in the last problem, just double that angle. So when we take this, drop it in here, we're just taking 9 pi over 8, multiplying it by 2 to get 9 pi over 4. And that's the actual input we'll be using for cosine. I should write this up. Now that I put equalities here, we should just fill that in. So whatever the angle is, double it to get the input here. That means the problem is almost over. We still need to put in the cosine value. We still need to simplify it, but this is the major work so far. We know we're picking the negative angle here, since 9 pi over 8 takes us to this quadrant. So we'll be using this angle, negative. Let me maybe highlight it slightly different. Next thing we need to do is just determine where is 9 pi over 4. But that's not so bad either. You can start drawing out all the multiples of pi over 4. They go by odd multiples. So here's 3 pi over 4, 5 pi over 4, 7 pi over 4. We're doing more than 2 pi over rotation then for 9 pi over 4. And it rotates from here all the way up to here. So this one is coterminal to pi over 4, 9 pi over 4. So that's just a full-on plus a 2 pi to get all the way back to here. That means cosine 9 pi over 4 is the same as cosine pi over 4 due to periodicity, and it turns into a square root 2 divided by 2, which is this value down here. So that's all that's going to substitute into this position. And now we have that this is equal to negative square root 1 minus square root 2 divided by 2. Divide by 2 again. And now we just have to simplify this thing down. We can use the same trick as before. Let's clear this denominator right here, just to make the numerator inside the radical sign a little bit more simplified. So multiply by 2 over 2, use the distributive law, and sine 9 pi over 8 is now negative square root 2 minus the square root of 2, divide by 4. And then it simplifies even slightly further. This becomes negative square root 2 minus root 2, divide by the root of 4. So negative root 2 minus square root of 2, that's definitely the awkward part about this, over 2. At least the denominator kind of came out nicer in this problem versus the last one. So if you really wanted to, you didn't have to settle for multiplying or dealing with 30-degree multiples of pi over 6, pi over 3, 5 pi over 6, 7 pi over 6s. You can now go by 9 pi over 8s if you really wanted to. You could do all the multiples of pi over 8 completely around the unit circle and start getting these values out. But I think you'd all agree that's a lot of work. And just for the sake of having really readily easy to calculate values, that's why we only did the multiples of pi over 6. We didn't deal with the pi over 12 or the pi over 8. It's just too much stuff. And they come in pretty complicated looking ways when you try to get their exact values. But that's the conclusion of working through these half angle formulas. Really, once you get the hang of how they go, it's really just a matter of finding what sign you terminate in to get the right version of the plus or minus. And then use these kinds of tricks to simplify them down. They're not too bad. They just look awful the first time you see them. Well, any questions whatsoever, folks, with the half angle formulas? Okay, well, after the half angle formulas are the next batch, the so-called reduction formulas. But the great thing about the reduction formulas is really all that's going on here is we take these identities and literally just square them. If you square this, you get this version. Square this one, you get this version. And I didn't square this one. To get the tangent squared identity, I just took the sine version, divide by the cosine version, divide by 2's cancel out. And this is one way to write the tangent squared version. It looks kind of weird because the angles are theta and 2 theta, whereas over here it was theta divided by 2 and theta. But this is really the same kind of concept. Whatever angle you have right here, you move over to the next one by just doubling whatever the angle happened to be. So double this angle, and you're using the identity right. There's no pluses or minuses because if you square both sides of these identities, this one and this one, plus and minus just vanishes. So really the reduction formulas, it's really just the half angle formulas in a slightly different format. Probably the major question is, why would you ever want to use the reduction formulas? And why is it called that? The idea with the reduction formulas is what you're reducing is the power. So this has a really specific context where it might come up. In calculus, pi even powers of sine and cosine are complicated in certain contexts, namely something called integration, which loosely integration is finding the area under a curve. And somehow the right-hand side is easier in that concept in calculus than the left-hand side. That power was odd. That's really weird. The odd power, sine cubed, is an easier expression, but high even powers are very difficult to work with. So if you know you're taking calculus, in particular calculus 2, this is something that you will very, very likely do in the very first 4 weeks of the semester. Dealing with sine to the power 4x is not an easy time. So what we want to do is rewrite this whole thing, reduce the power, so that there's no trigonometric expression there with an exponent higher than 1. So really, we're just going to use reduction formulas over and over again until the power 4 becomes a power 1. So this is the context on where it could come up. I feel like it's a good idea to mention the context because when we reduce the power, the result we get is more complicated. But whether something is complicated or not depends completely on the context. So that's why we're doing this kind of problem. Just another look at these kinds of identities and more practice with trigonometry. So to start it out, let's just copy in sine power 4 of 8x. There'll be a couple of problems just like this in the homework as well. And that power 4 is kind of tricky to deal with because these are powers too, all three identities. So first we just use an exponent law to break this down. This can now be re-expressed as sine squared of 8x squared. That's a valid technique to take. The power 2 as an outer exponent just multiplies these exponents together to get back the original sine power 4. Then we use the identity, this one here, on the function that's on the inside, the base sine squared ax, 8x. Let's write that out on the margin to see how it plugs together. Sine squared of 8x will turn into this thing, 1 minus cosine divided by 2. Anyone see what the angle should be right here? Yeah, good call, Luke. Whatever it starts with, just double whatever the result is. And like you said, it'll turn into a 16x right here. And really, that's kind of just the heart of the reduction formulas and the half angle identities as well. So let's drop in 16x. And same idea as before, just double whatever that input is. So this whole 1 minus cosine 16x looks more complicated, but the power is 1, so that's what we would like. Except it plugs back in here, and we still have to square it. But we're getting down to what we'd like to get. So this on the next line is equal to 1 minus cosine 16x. Power has been reduced. Now the whole thing is to power 2. We can square numerator and denominator independent of each other. So we have 1/4 squaring the denominator, square the numerator, 1 minus cosine 16x. And we're really just using this squaring formula. A minus b squared is a squared minus 2ab plus b squared. And don't let me forget the power 2 there. So let's FOIL this out just through this identity or this idea here. And this comes out as 1/4 multiplying first 1 times 1 for a 1. Then we FOIL be 1 times negative cosine 16x, but you get 2 copies of that. So altogether, negative 2 cosine 16x. Then the b squared is just taking negative cosine 16x multiplying by itself to get positive cosine squared 16x. So let's distribute the 1/4 through. Notice we still have a problem. Like we mentioned, there's still a power 2 there we have to resolve. But at the moment, this is 1/4 minus 2 times 1/4, or 2/4 cosine 16x plus 1/4 cosine squared 16x. So now we need to run an identity through this one. That'll just be the second identity down below, or I guess that's up above, rather. So let's write it in our form that we see it. We have cosine squared 16x becomes 1 plus cosine. Like we mentioned before, whatever your input happens to be, double it. So this time we get 32x. And we divide by 2. And same concept as before. Whether it's the reduction formula or the half angle formula, really the only difference between these are the inner signs, negative to positive, for sine to cosine. So that whole thing gets plugged in right here. And now we're almost through the algebra, just a couple more substitutions, distributions, and we'll have our result. We can reduce this fraction to a negative 1/2 cosine 16x plus 1/4 times the group 1 plus cosine 32x. And then this is all divided by 2. So going further, let's scroll a bit for just for the extra real estate. We have 1/4 minus 1/2 cosine 16x. This 2 here can factor out to multiply the 1/4. So now it's a 1/8. But we've got to put a sign in the middle. Let's start by plus 1/8 times the group 1 plus cosine 32x. Then the 8th distributes inside. So we have 1/4 minus 1/2 cosine 16x plus 1/8 plus 1/8 cosine 32x. And one last thing to do, we have like terms from here to here. That's 2/8 really, with the like least common denominator, plus 1/8. So this is altogether 3/8 minus 1/2 cosine 16x plus 1/8 cosine 32x. And again, it's kind of wild that in the context of calculus 2, this is the actual monster. This is the one that's harder to deal with. And the thing that we got to our eyes, which looks like a mess now, that's the easiest thing to deal with in the context of integration. Really, for us, it was just an opportunity to practice these identities one more time. And I'm just mentioning it fits into a larger context so it doesn't feel like we made something needlessly complicated out of nowhere. It really has a use. We did it, folks. We followed the instructions to the letter. We took sine power 4 of 8x and wrote it with an exponent no higher than 1. The inputs got large 16x and 32x, but the exponents on both are exactly 1. Well, any last questions or comments, folks? Finishing out that last example here. The 1/4. So let me take a look. So I had a 1/4 that came from here. Oh, I got you. So that was from this step here where I squared out the numerator, 1 minus cosine 16x. But then it was the denominator squared for a 2 squared, and that's where that initial 1/4 came from. It took a little bit digging to see where it actually resulted from. Does that make sense on where we got that 1/4? Yeah, absolutely. Other questions at the moment? Okay, let's save up these notes. Next, we're going to move over to the next section. This will be our last section for chapter 7. We're going to look into the idea of solving trigonometric identities next. I have 7 different examples we're going to look into, which covers the kind of similar problems you're going to see in the homework assignment as well for section 7.5. First, I wrote down just a little bit of notation. We often write down this symbol right here, R, to represent all real numbers. In interval notation, it's the interval from negative infinity to positive infinity. But really, the major thing I wanted to write down as a quick symbol is this symbol Z. This is the set of all integers. Comes from the German language where Z is the first letter for the word for number. So we use Z to denote all integers. So the positive integers as well as the negative integers. Likewise, R is just a shorthand for all real numbers. And just because of completeness, this fancy C right here would be the set of all complex numbers. We'll get a little bit into complex numbers on the very last part of chapter 8. But the reason I want to emphasize Z is because it actually comes up in these notes. It comes up in the context of finding all solutions to a trigonometric equation. So the major issue with trigonometric equations are if there is a solution, there's often infinitely many solutions. The reason for that is cosine is a periodic function. Let's write this information here. Cosine x, or just cosine, is periodic with period 2 pi. This means cosine of x plus 2 pi times k is just cosine x, where k is any integer. So k could be 1, and it's just cosine x plus 2 pi, or it could be -3 or -5. Any integer value inside here is going to give us just ordinary cosine x. So the statement k is any integer, you could just abbreviate to saying k is in z. And that's where the set z comes into play. I'll often just write down k is any integer. If you like shorthands, this is a decent one. And z does come up a lot in other classes as well, so it's a good one to think about and introduce into these notes. So let's go and solve our very first bona fide trigonometric equation, that cosine x is negative square root 2 divided by 2. I think you'll like the idea because it's kind of similar to what we do in section 6.3 on inverse functions. In fact, we'll use inverse functions on the very end of these notes, where the numbers are a little bit more awkward. Like if the right-hand side was a negative 1.7, we can still solve it, but we need to use cosine inverse. Or maybe not negative 1.7, maybe negative 0.7, so it's in the actual domain of cosine inverse. But here's how this problem would start. We go down and write down a unit circle. We take the right-hand side, negative root 2 over 2, and place these values somewhere. Well, because this is a cosine value, the somewhere on this one would be on the x-axis, right here, negative root 2 over 2. Then we just come up with what angles can we take cosine of to get negative root 2 over 2. There's one angle up here. This one is pi over 3 pi over 4. But there's another angle down here. This one is 5 pi over 4. So we know you can plug in cosine at 3 pi over 4 or 5 pi over 4. It's definitely negative, and it turns into exactly negative square root 2 over 2. But that's just two solutions. So this is where k being a useful concept, and this x plus 2 pi k is also important for us. Here's what this looks like geometrically. We have y equals cosine x. It's a periodic function, so it's repeating infinitely many times at all values between negative 1 and positive 1. We have a value between those ranges. We have y equals negative square root 2 divide by 2. And here's one solution, 3 pi over 4. There's another solution, 5 pi over 4. But if you go backwards, here's another solution, negative 3 pi over 4, another one, negative 5 pi over 4. And there's infinitely many more. We can just keep on tagging them. I can't just write down every single one of these that occur in a nice compact way. So we're going to use this periodicity equation right here, x plus 2 pi k. So solving these equations just amounts to finding these solutions on the unit circle that make this come out to negative root 2 over 2. Then we can say the solutions are x equals 3 pi over 4. But you can add and subtract, or let's just say plus, because if we use k, it can have a negative or positive value. You have to add, take the period 2 pi times k. And all we're using is this idea right here from periodicity. Values repeat like this, and we can say, or x equals the other solution, 5 pi over 4, plus 2 pi times k. So both branches give us infinitely many solutions. Like we mentioned before, if we go to this one, 5 pi over 4, we'd be on this end, that solution. If k is, say, 3, that means we'd be wrapping one time, that's plus 2 pi, another time, that's plus 4 pi, and then another time, that's plus 6 pi, but we end up on the same spot. So we would still get negative root 2 over 2, and it would check in the equation. So cleanest way to just state all solutions is just say x is the first solution we found, plus 2 pi k, periodicity, or the second solution we found, plus 2 pi k through periodicity, where k is any integer. So solving trigonometric equations is kind of weird because periodicity sort of muddies the water a little bit, but it's all about finding their solutions from 0 to 2 pi, and then just adding the periodicity parts we see right here and right here to give all solutions. So this is kind of our warm-up then in looking into solving trigonometric equations. We'll look at several others when we come back on Wednesday's class, And likely we'll finish this off after our exam 3 that we have next Monday. But any last quick questions on getting through this one, what equation solving looks like at the moment? Okay, well, have a great night, folks. We'll return here, talk a little bit more about exam 3 when we come back on Wednesday's class. I'll see you all next time. See you Wednesday. You bet. Take care.